Okay, now we're going to talk about the forces on a control volume. So there's some of those forces that we have in our equation. Several different types: pressure, shear, gravity, other forces. Let's go through each one of these, starting with pressure force. A pressure force, we're going to get a net pressure force whenever we have an uneven pressure distribution. So let's say our pressure distribution looks like this. You can see on this left-hand side we got bigger pressure, so we would get a net force to the right in this kind of situation. This is our pressure field. So in the most general case, you would actually have to integrate in order to find the net force. And you would integrate PdA. Right? So you'd have your differential area and the pressure on that area, and just like you did with shear stress, you could integrate over that whole surface. But our force, our net force, is going to end up having a direction. So actually we can use, if we have all different directions like this, we can use our normal vector in order to give us direction. So in the most general case, we're going to get some of the pressure forces, or pressure force, net pressure force, is equal to minus the integral over the control surface, P times N dA, where N, again, always goes out, and therefore that's why we have the negative sign right there, because N always goes opposite pressure force. Okay, if the pressure is uniform all the way around that object, we're not going to get any pressure force at all. And also we can add or subtract a constant pressure over our whole control volume as well. So if, for instance, we have atmospheric pressure acting on part of our control volume, we can just subtract atmospheric pressure from everything and end up using gauge pressure, just like we did in the curved surface and flat surface type of problems. Okay, so for example, if we have the force on a nozzle like this, so we have absolute pressure here on the left-hand side, and then atmospheric acting everywhere else, what we can do, subtract off that atmospheric off of everything, and what we're left with is just gauge pressure. Okay, so same kind of thing. Now we don't usually have the situation where we have to integrate the pressure all over the surface in order to figure out what the net force is. Usually we have what we have here, and that's just a constant pressure. And in that case, our force is just pressure times area, right, when you have a constant pressure. And you can look at it to figure out which direction that pressure is going. Okay, so in this case, above, so for this example, our pressure force would be Fx, and, or let's just say our pressure force here as a vector is equal to 25 psi, it's really psig, and then times our area, which would be pi over 4 d squared, and that would be in the I direction. Okay, and that's the way you're usually going to do this. Fairly simple. Okay, something we're going to use a lot is the fact that if you have some flow that is open to the atmosphere, for instance, a flow coming out of this nozzle and into air, it at that point where it comes out, it is going to become atmospheric pressure. Inside of here, it can maintain some other pressure, but outside it's going to be atmospheric. We'll use that a lot. Okay, so be careful with that. I'll put a little star by it. If it's open to atmosphere, kind of like our jet hitting that flat plate or that curved plate. It's open to atmosphere, P equals P atmosphere. And if we're using gauge pressure, which we usually are, that means 0. Okay, shear force is the next one. So we've done pressure force. It's usually just pressure times area. You can see, if you have a free body diagram, you can see which way that's going to go. Always pressure forces always point towards your control volume, right? And normal to your control volume. Shear force, the next one. Shear force is the integral over your control surface. Remember, this is the parallel part of tau, and tau actually has two arrows on top of it, dot n dA. Okay, and that's because if you're talking parallel can actually have two directions in your coordinate system. Tau can have two directions in the coordinate system, and then you have three different coordinates in coordinate system, which is why you end up with 6-component matrix as opposed to a vector. And as you can see, this probably gets pretty complicated. So what we want to do is avoid it, and the way we normally avoid it is draw our control volume so it's perpendicular to the velocity, or out in the air where there is no velocity. The other option is to make it the unknown that we're solving for, and we'll actually do that at some point when we get to pipe flow. But for now, just make sure you draw your control volume outside, so you'd never draw it in here. Don't do that. Let's see, so don't do what I just did. Instead, you draw your control volume a big box like this. That's what you would want to do. So it's zero shear stress all on the outside of here and where it's perpendicular to the flow. All right. Next we have body forces, and body force is just the weight. Okay, so gamma V for the fluid that's inside your control volume, and then plus any solids that are inside there as well. So the weight, and that'll give you your body forces. Other forces then, that's the last one, and that's where our control volume cuts through a solid. So in our original problem with the disc, where the jet of water was hitting the disc, that was where we found F bolt. Okay, so this would be where it cuts through bolts, ropes, whatever, any solids. There we're going to have a force, and that's going to fall under the other forces. So summing all these up, because we have forces from all of these things, our sum of our forces is sum of our pressure forces plus some of our shear forces, which hopefully are going to be 0, plus some of our body forces, which is weight, plus some of our other forces, and a lot of times that's what we're solving for. Okay, and that sum of the forces, again, if we're doing the simplest case, steady state, incompressible, average velocity, fixed number of inlets and exits, what we end up with is the sum of the forces equals the sum over the outlets or exits, m dot v, minus the sum over the inlets, m dot v. And again, those are vectors, so break it into components, x, y, and z, and then solve. Okay, and the sum of the forces then is this. Okay, and remember, you use this form if you have a non-accelerating CV. Non-accelerating. If you did have one that could accelerate, say it's some sort of rocket or something like that, then what you would do is just pull these over to the other side. So you'd have the sum of the forces minus sum of m dot v out plus sum of the m dot v in equals mass of your control volume times acceleration of your control volume. All right. Won't use that much, but it's certainly possible we could end up using that. Okay, so one other quick example. We did the examples before using the flat plate and the jet of water. All our pressures in that case were 0 because it was all open to the atmosphere and we could use gauge pressure. In this case, we have internal flow, and that's going to make it a little bit different. So let's just go quickly through how we would solve this problem. So what this is a reducing bend. So we've got flow going in, coming around here, and then going back out that direction. Okay, and what we want to find is the total force in the flange bolts. Okay, and there's supposed to be bolts here. So first thing, let's draw our control volume. What we want to do, remember, you want to draw perpendicular to the flow. And we want to cut through wherever we're trying to find things. So let's cut through these bolts. So I would cut through the bolts right here and right here, and that's perpendicular to the flow. In between, doesn't matter, just don't go in here. Instead, go all the way around. We don't want to cut through this pipe over here either, because that, first of all, would create some shear. And second of all, that would give an other force that we don't want. Doesn't really matter what this looks like out here because it's all just at atmospheric pressure and no flows going on out there, so you don't have to worry about it. Assumptions, we're going to do our basic simplifying assumptions as much as we can. Since what we want to do is decide up here by looking at our givens whether or not we're going to assume average velocity. What we're given is Q and we're given diameter, so we're going to have A's. We don't have any kind of velocity profile. A velocity profile would be like something like some velocity times r squared minus r over r kind of thing. So it'd be an expression somehow. So we don't have that. What we have is a Q as a constant, and we have areas, which means we're going to use average velocity. Okay, and so we're going to use that simplest case. Sum of the forces equals sum, and we don't have an accelerating control volume, so sum of m dot v out minus sum of m dot v in. All right, so we have one inlet exit, so we're going to be able to drop these sums. What we know about mass flow rate is that oh, I got to number these things. Oh my gosh, get myself in trouble. We got to number our inlet and exit. So 1 is our inlet, 2 is our exit. We can say m dot 1 equals m dot 2 equals m dot. That's our conservation of mass for this one. Pretty simple. Since it's incompressible, also we can say Q1 equals Q2 equals Q. And that is going to give us our velocities that we need, because you see we don't have any velocities. So let's simplify this a little bit. Sum of our forces equals m dot. So m dot's constant, I can pull it out, and there's only one inlet and one exit, so V2 minus V1. Let's make that a vector. Now what you want to do is break it down into the x direction. X direction is our main direction. Fx equals m dot, and if we're just using xy direction here, we can say, if these are our coordinates, rectangular coordinates, our I direction, our x direction velocity is u, so u2 minus u1. All right, so let's figure out what these u's are. u1, okay, it's going in the positive x direction. See, I have this positive x is my coordinate system down here, so that's going to equal positive q over a1. Now be careful when you're finding velocities, your a has to match where your u is here, and that is going to equal v1. R2, it is going in the negative x direction, so minus q over, and again these have to match, the a has to match the u, so don't put a1 there like I just did, and that's your v2, only minus v2 if v2 is our average velocity without direction. All right, so let's go down here and let's draw a free body diagram. I already have a diagram here, so again, x is this direction, y is this direction. We're going to have forces. We got a force of weight for all of this plus all the others, all the metals, okay, in the y direction. Add our bolts. Let's lump all our bolts together and just call it Bx and By. All right, we would have to worry about them if we were summing moments, but I think in this case we're going to not have to sum moments, so we can lump those all together. Our F shear with our control volume is equal to 0. B, we're going to say again, is all bolts. Okay, so what about those pressure forces? So we have pressure forces, shear forces, we have body forces. We already took care of shear and body forces. Pressure forces. Since this is internal flow, we do have pressure here that we have to worry about at 1 and at 2. And the pressure force, FP1, would be that. And FP2 always towards the control volume. All right. So here's your control volume going through here, FP2. Okay. We also might want to draw our V1 here and our V2 here. Okay, but I think we got all the forces now. So in the x direction, our sum of the Fx equals Fp1 plus Fp2. They're both, remember, both going towards the control volume. They're both going in the positive x direction. Plus the way I drew Bx up here, Bx equals then what we have, m dot times minus V2 minus V1. Okay. So FP1, okay, we don't have some kind of varying pressure all over that. What we're told is 350 kilopascals at 1 and 120 kilopascals at 2. By the way, lower pressure at 2 because of higher velocity at 2. So FP1 is just going to be P1A1. Remember, use the corresponding area for what you're talking about, and that's at the inlet. FP2 is going to be P2A2. Okay, our m dot is rho times q. We're given q, so we can leave it like that. Our V1 is going to be q over A1. That comes out to be 2.2 meters per second, if you want to check. Our V2 is q over A2. Comes out to be 21.2 meters per second. All right, again, higher velocity because we have a smaller area at 2. Also why we have a smaller pressure at 2. So what we're going to end up with, we're going to try to solve for Bx. Minus P1A1 minus P2A2 minus m dot V2 plus V1. Okay, a bunch of minuses. So I obviously drew B in the wrong direction. Bx is minus 14.9 kilonewtons, and that will be, means it goes to the left. Okay, and we have the velocity is going to push it to the left. So here the velocity coming in is pushing it. So the velocity is pushing it to the right. The pressures are pushing it to right. So the bolts have to counteract that to keep your control volume still. And that's why the B is to the left. Okay, so velocity here pushing it to the right as it comes in. Going out, since this V2 is going out, it is also pushing to the right. And both of our pressures also pushing to the right, thus they all had the same sign, all those negative signs. Okay, in the y direction then, the only thing we've got in the y direction is By and W. There's no velocities going that way, no pressures going that way, so By is just going to equal our weight. So the weight's going down, the bolts have to hold it up. And that weight equals water plus elbow. All right, so that's all I got for today. Go ahead and finish up your quiz. And sorry it was a long one, but there's a lot to go over in this. Talk to you later. See you in class.